modern people live in a space surrounded by varied and ever more complex equipment which provides them with a high standard of living. Providing such a high standard of living requires the uninterrupted operation of sophisticated technological processes. We need to provide heat, light and energy from various suppliers. These processes, which are concomitant with modern life, are not merely complex but also dangerous by definition. If the supply of energy is broken at any moment, it can cause significant harm. The probability of such an unfortunate outage depends to a great extent on the people who ensure the uninterrupted and safe operation of equipment. It is important to plan and organize their work, to have a thorough and professional selection process, and also to train them and keep their qualifications continuously up to date. How should we organize modern education? It is no secret that people carry habits that they have learned from education into the workplace. Which habits does modern education instill? In the academic institutions of antiquity, students acquired not just knowledge, but also the ability to reason independently. The basic method of instruction was discussion. University lectures in the Middle Ages, where notes were taken from speech, were, as could be said today, the most economical method of increasing the reserve of books available to students, as all books were handwritten and extremely expensive. In our time, educational technology has come a long way from the goose quill, ruler and paper, and the possibility will become available to give students the skills which will be demanded in the workplace, whether they are creating new technology, managing complex systems, or monitoring complicated technological processes. Current technology gives us totally new possibilities for education. We have long known that simply taking notes during lectures allows us to absorb more than 10% of the information, while involving students in the solution of complicated problems allows the absorption of up to 90% of the essential knowledge and skills. In this film, we'll talk about one of the attempts to fully realize the potential of current technological methods in the education of energy transport specialists. In Samara Technological University, the integrated educational course Pipeline Supply of Oil was implemented. The course was based around a detailed mathematical model of the entire process, which was turned into a spatial map of the process. The state of the equipment and the working scale model constantly changes, which is indicated by a change in the color of illumination. Water flows in transparent pipes to imitate the real movement of oil. Sections where liquid is currently flowing are lit up, literally showing the process of oil transfer. The technical schematics depict the movement of oil through the sections of the main pipeline from tank to tank on one main and two intermediate workstations. The tanks are shown with multiple views, including a display with normal tank performance and a simulation of tanks with floating pontoons or floating roofs. The fluid level in tanks constantly changes and is fully described by indicators. Oil is transferred from the tanks along a line of main and supporting pumps at the exit of the main pumping station. All of the basic equipment is simulated and shown. Filters, oil measurement units, pump aggregators, pressure regulating sections, input, output, diagnostic and cleaning chambers, the cleaning and diagnostic substances themselves, support systems and other equipment. In this kind of module, the participants are involved in the production process from the very start, familiarized with various types of equipment, and have the chance to regulate the process from a highly realistic workstation for a direct and immersive experience where they can see the results of their decisions immediately. Such training gives by far the best results as the trainee is surrounded by realistic information with every physical parameter properly represented in itself and with respect to other parameters. Apart from the visual effects, the student gains the most important kind of knowledge: how the process works, how the equipment is laid out spatially, and how all of that is connected to the dynamics of the process. Parameters which are not visually observable are depicted by various graphs and diagrams on both the external screens and the students' workstations. In this way, training progresses from simple to complex, from general familiarization with the characteristics of the technology and equipment to the principles of directing the automated systems and to the ability to take part in complicated operations in non-standard conditions. In this integrated module, we have employed the principle that there should be no blind spots in the preparation of specialists. So the physical parameters can be directly measured with real meters, and real equipment can be directly observed on the test bench, down to the simulation of real automation algorithms on actual controllers. In this way, general lectures for energy transport specialists can be given, and by using the scale model and screen to illustrate details, different paths can be indicated on the model with a laser pointer, with the support pages and 3D animations, the training pages on those paths displayed on the screen, all in a single classroom. Here we can deepen the practical knowledge of professionals working with complicated technical measurement and animation systems. The controllers can be programmed in order to experiment with different working algorithms for animation, and the result is immediately visible on the working scale model, as it works with the same data in a single mathematical model. Future engineers and dispatchers can be trained to manage complex technological processes in real time, both in normal conditions and in non-standard situations with abnormal stresses, and even investigate different working conditions and ergonomic influences on perception and reaction time. The students themselves can take part in the design of the applied provision, change algorithms and interfaces, expand the technical chart, change the layout of the pipelines, and even investigate completely different systems beyond the limits of the tanks, as the constructor of the mathematical model is open to users. To simulate more complicated scenarios, there's a special emergency event generator, which compiles isolated failures in a dynamic chain which unfolds an abnormal situation in space and time. These situations can even be stored in an archive and replayed. Students can be assessed with methods and testing programs which are constantly being refined. Records showing the consistency of their performance, like on a training machine in the gym with the latest automatic grade for that performance. This program is so effective in training due to the fact that the process of education is more natural for people who are accustomed to working with audiovisual, spatial and symbolic methods of interaction, which allows the trainee to choose a method to achieve the best absorption of information, seeing, hearing or experiencing, or most importantly, to take part in situations and perform tasks which could only be encountered otherwise through years of experience in the field. This experience can result in mistakes which are unacceptable on a real site. Preventing these future mistakes was one of the main intentions in developing this course. These working principles, technical decisions and program provisions can be used for the development of similar systems for the education of specialists in areas such as refining, maintenance and management of oil and gas transport and extraction equipment, electricity supply, communal urban services and transport infrastructure, and perhaps others.